Hello everyone, we are solving question number 53 of GATE 2020 Chemical Engineering, and the subject is Process Control and Instrumentation. The question is, consider the following closed loop system where GC, GF, GP are the transfer functions of controller, final control element and process respectively. Y and YSP are the response and its set point respectively. For a gain margin of 1.6, the design value Kc is dash. So in the given question, we have been provided a closed block diagram for closed loop system, and we have been asked to find the controller gain, that is the value of Kc, for a gain margin of 1.6. So let's take a look on the solution. So here we have been given a gain margin and have been asked to find the value of Kc. So how do we define gain margin? So we define this gain margin as the inverse of the amplitude ratio at the phase crossover frequency. That is, we can write this as gain margin is equal to 1 upon amplitude ratio at omega equal to omega C0, where this is phase crossover frequency. And we define this phase crossover frequency by equating the phase lag, that is phi overall, with minus 80 degree. That is the frequency at which the overall phase lag is minus 180 degree is this crossover frequency. So to find the gain margin, first we have to find this crossover frequency. So we will do that. So the overall phase lag of this transfer function, let's just write the transfer function as G open loop will be GC GF into GP. GC we have been given as Kc, GF, the transfer function of final control element, is 10 upon 0.1 S plus 1, and for GP, for process, the transfer function is 1 upon 0.1 S plus 1 whole square. We can simplify it, that is the open loop transfer function as 10 Kc upon 0.1 S plus 1 whole cube. Now, given this open loop transfer function, we have to find the phase lag, that is phi, and equate it to minus 180 degree to find this crossover frequency. So let us write this phi overall is equal to minus 180 degree, and it will be the summation of all this, the phase lag of all these three individual transfer function. That is, you can also write this as minus 180 degrees equal to phi of, let's say, C phi of F plus phi of process. So since this is a constant, the phase lag will be 0, and for this we already write the open loop transfer function as the for this entire system. We already found the open loop transfer function as 10 times Kc upon 0.1 S plus 1 whole cube. So for this Kc we already wrote it as 0, and for this 1 upon this entire thing, 0.1 S plus 1 whole cube, we can write this as, basically it will be 3 times of the phase lag of the first order system with time constant of 0.1. So that will be 3 times of tan inverse omega tau, where tau is 0.1. So let's just replace it, 3 times tan inverse omega into 0.1. So from over here, we can write this as minus 60 degrees equal to, this will be tan inverse minus omega tau. So it will become tan inverse minus of 0.1 omega. That is, we can write this as tan 60 is equal to 0.1 omega. So omega, that is a crossover frequency. In this case will be 1060 root 3. So 10 times of root 3. So this is our crossover frequency. Now we need to find the amplitude ratio at this crossover frequency, and by using this gain margin we can find this value of Kc. So that is, we define this gain margin as 1 upon amplitude ratio as omega equal to omega C0, and this gain margin we have been already given as 1.6. So we can write this amplitude ratio is equal to 1 upon 1.6, and now we need to find this amplitude ratio. So that is, amplitude ratio is equal to 1 upon 1.6, and for this, again, for this open loop block diagram, for each of these individual block, the amplitude ratio will be the simple multiplication of the amplitude ratio of this individual block. So that will be Kc. We can write this as AR1 into AR2 into AR3 is equal to 1 upon 1.6. That is Kc into 10 upon under root of 0.1 omega whole square plus 1 into 1 upon the root of 0.1 omega whole square plus 1, and since here we are having this square, so this will be again square. Ultimately this will become 10 Kc upon 0.1 omega square plus 1 raised to 3 by 2 is equal to 1 on 1.6. So now this omega value we already have calculated it as 10 root 3. So we can replace it over here. So this will become 10 times Kc upon 0.1. This will be 1 root 3, that is 3, 4. 1 3 by 2 is equal to 1.6. So 4 upon 3 by 2 will be 2 raised to 3, that is 8. So Kc will be 8 upon 10 into 1.6. So the final value of the controller gain, we can write it as 0.5. That is 8 upon 16. It will be 1 by 2, that is 0.5. So for the gain margin of 1.6, the design value of Kc is 0.5 is our final answer.